Dear students, very good morning. Today we will discuss nucleophilic substitution reactions of alkyl halides. Why alkyl halides exhibit nucleophilic substitution reactions? The first one is that the bond between carbon and halogen is polar. The carbon gets positive charge and the halogen gets negative charge. Here the positively charged carbon is acting as electrophilic center and there is a possibility of attacking of nucleophile, that is electron rich species, on the electron deficient carbon. This is the first reason for exhibiting nucleophilic substitution reactions by alkyl halides. What is the second reason? The second reason is that halogens are good leaving groups. We know that halogens are most electronegative elements in their respective periods in periodic table. As the electronegativity increases, basicity decreases. As basicity decreases, the leaving ability of the groups increases. Since halogens are most electronegative, they are less basic, so they are very good leaving groups. Due to these two reasons, alkyl halides exhibit nucleophilic substitution reactions. Then, what factors can influence the leaving ability of the groups? The first one is electronegativity, the second one is size of the groups, and the third one is resonance. As the electronegativity increases, basicity decreases and the leaving ability increases. In periods from left to right, there is an increase in electronegativity, so there is a decrease in basicity, so there is an increase in leaving ability of elements. If we take carbon, nitrogen, oxygen and fluorine, fluorine is more electronegative than oxygen, than nitrogen, than carbon. So the basicity order will be carbon is greater than nitrogen, nitrogen is greater than oxygen, oxygen is greater than fluorine. The leaving ability order will be reversed to the basicity order. So in this case, fluorine has more leaving ability than oxygen, oxygen is greater than nitrogen, nitrogen is greater than carbon. Let us consider effect of size. In groups from top to bottom, there is an increase in size of atoms. So, when there is an increase in size of atom, there is a decrease in basicity. So, when there is a decrease in basicity, there is a increase in leaving ability of the groups. If you take fluorine, chlorine, bromine, iodine, from fluorine to iodine there is an increase in size, so there is a decrease in basicity. So the basicity order will be fluorine greater than, chlorine greater than, bromine greater than iodine. So the leaving ability order will be iodine greater than, bromine greater than, chlorine greater than, fluorine. Suppose if you take the conjugate basis of these elements, if you take F minus, OH minus, NH2 minus, CH3 minus, the F minus has higher leaving ability when compared with the other bases. If you take I minus, Br minus, Cl minus, F minus, I minus has higher leaving ability when compared with other groups. So, in periods from left to right, there is an increase in leaving ability. In groups from top to bottom, there is an increase in leaving ability. Among halides, iodine has higher leaving ability when compared with other halogens. Resonance decreases basicity and increases leaving ability of the groups. Due to resonance, the groups will be stabilized and the electrons and the groups will be delocalized. So the ease of donation of electrons will be decreased. So the basicity of the group will be decreased. Finally, there is an increase in leaving ability of the leaving groups due to resonance. Generally, alkyl sulfates and sulfonates and also aryl sulfonates are acting as very good leaving groups. Mesylate, triflate and tosylate, these are the most commonly used leaving groups in organic synthesis to get best yields. Then what is mesylate? Mesylate, this one is methyl sulfonate, and triflate is trifluoromethyl sulfonate, and tosylate is toluene sulfonate. This one is a derivative of toluene sulfonic acid. Okay, these are best leaving groups. These are used in organic synthesis to get best yields. The leaving groups can be classified into excellent, very good, good, fair, poor and worst. Here the sulfonates are acting as very excellent leaving groups. Triflate, tosylate and mesylate, these are very excellent leaving groups. Here N2, if you take azo group, N2 is the leaving group. This one is better than triflate, tosylate and mesylate in the case of leaving ability. And very good if you take I minus, halogen I minus is very good leaving group. And Br minus is a good leaving group. And H2O in H2O and ROH. Okay, these are the leaving groups we can find when alcohol is protonated or ether is protonated. And the next one is fair. Cl minus is a fair leaving group, and NH3. This type of leaving group we can find in protonation of amines. When there is a protonation of amines, you can find NH3 plus. This ammonia is a leaving group. And F minus is a very poor leaving group, and acetate anion also very poor leaving group. And the worst leaving groups are phenoxide anion, alkoxide anion, amides, and also alkyl carbanions. These are very worst leaving groups, and these leaving groups, when there is a presence of these leaving groups, there is no nucleophilic substitution reactions. In this case also, it's very difficult to perform nucleophilic substitution reactions when there is a presence of fluorine or acetate as a leaving group. So, in nucleophilic substitution reactions, generally we find alkyl iodide, alkyl bromide or alkyl chloride. This is the general representation of nucleophilic substitution reactions of alkyl halide. This is the alkyl halide, this is the nucleophile, this is the nucleophile substituted product, this is the leaving group. Here the carbon, this is a reaction center. Why it is called as reaction center? Since nucleophile attaches to carbon, this carbon, and also there is a leaving of halogen from this carbon. The reaction takes place at this center. That's why it is called as reaction center. These are the nucleophiles which are commonly used for the nucleophilic substitution reactions of alkyl halides. When you react alkyl halides with these nucleophiles, you will get different functional groups. When you react alkyl halide with the hydroxide anion or water, you will get ROH, alcohol. When you react with alkoxide anion, you will get ROR, ether. When you react with ammonia or amide NH2 minus, you will get amine. When you react with the ionic cyanide, potassium cyanide, you will get alkyl cyanide. When you react with the alcoholic AgCN, this one is a covalent cyanide. Here the nucleophilic center is nitrogen, that's why you are getting isocyanide, alkyl isocyanide. If you take alcoholic KCN, the reaction center, the nucleophilic center is carbon in the case of alcoholic cyanide. That's why you are getting alkyl cyanide. In the case of AgCN, the nucleophilic center is nitrogen, not carbon. So you are getting isocyanide. If you take covalent nitrite, that is AgNO2, here the reaction center is nitrogen. That's why you are getting a nitroalkane. Suppose if you take ionic nitrite, that is KNO2 or NaNO2, you will get alkyl nitrite. When you react alkyl halide with silver salt of acetate or carboxylate, you will get ester RCOOR. When you react alkyl halide with hydride donors, LiAlH4 or sodium borohydride, you will get alkanes. And when you react with alkyl magnesium halide or alkyl lithium or R2CuLi, you will get alkane. When you react with SH minus, you will get thiol. It means you can prepare numerous number of functional groups from alkyl halides by changing nucleophiles.